Welcome back. Today we're going to discuss two-dimensional motion. So last time we discussed one-dimensional motion, right? And we talked about scalars and vectors, and it got a little bit confusing. So before I bring in two-dimensional motion, I just want to review what a scalar and a vector are, just to make it clear. So a scalar quantity is one where it only has a value. So let's see that. Scalar. So what is a scalar? Like something like speed, distance, time. They only have a magnitude. So that's what makes a scalar quantity. This isn't going to change depending upon the dimension. It's always going to just be one number. And it's always going to be a positive number. All right? So that's a scalar quantity. Now a vector quantity, on the other hand, has two pieces of information. A magnitude and a direction. All right? So this magnitude is, again, just a number, like the scalar. But then this direction, it can vary depending upon how many dimensions you're in. So let's think of an example of a vector quantity, like velocity, right? Velocity is a vector quantity. Displacement is a vector quantity. Acceleration is a vector quantity, right? Well, these are all vector quantities. All right, let's talk about direction, though, a bit. So in one dimension, when we talked about 1D, motion was constrained to be on a line, on a single line. So let's say if you have velocity of 5 meters per second, what that looks like is, if this is your number line, let's say this is 0, 1, 2, 3, 4, 5, then the vector is actually just this arrow that goes from 0 to 5. And let's say now the velocity is negative 1 meters per second. Well, now it would be somewhere over here, your arrow, right? Moving in the opposite direction. That's where negative 1 is. So in one dimension, this arrow, which represents our vector quantity, has to lie along this one line. Let's look at two dimensions. In two dimensions, things get a bit more interesting. In two dimensions, you have two lines now. And now we can't just say positive or negative. We have to specify. So let's say this is the x-axis, this is the y-axis. Well, maybe we have to say, okay, 3 units for x. So I'm going to say 3 for x and 2 for y. What does this mean? Okay, so 3 for x means I'm going to jump 1, 2, 3, and then 2 for y means 1, 2, and that's my final point starting from the origin, and that's my vector. Whatever this 3, 2 quantity represents. This is my direction, right? This is a direction. What about my magnitude? What's the magnitude over here? We have two numbers. Which one do we choose? Is it 3? Is it 2? It's neither. The magnitude is just the length of the arrow. So it's, if you remember Euclidean distance, you would do 3 square plus 2 square root. Or if you like to think of it in terms of a right-angled triangle, that's 3. Okay. Let me try to use a different color. That's 3, and that's 2. And that's the hypotenuse. So if you remember, a squared plus b squared is equal to the hypotenuse squared, or you can think of it in terms of distance formula, whatever helps you, understand this. So 3 squared plus 2 squared, that's 9 plus 4, and that's square root of 13. That's the magnitude. So the magnitude is square root of 13, the direction is 3, 2. Jumping back to the previous problem where we were in one dimension, here the direction for the red line is positive, and the magnitude is just 5. For the negative 1 meters per second, the magnitude is just 1, because we don't care about signs, and the direction is negative. You see, we separated the magnitude and the direction. They look like they're one sort of quantity in one dimension, but they're actually two separate things. In two dimensions, it's more easy to actually distinguish. We can see that, oh, this is the direction because it's like a pair. It tells me which direction according to the x and y axis. And the magnitude is kind of like the sum of the two. So I can have another vector that's square root of 13, but the direction is different. So I'm going to draw another arrow. Okay, 1, 2, and let's say that this is 1, 2, 3. And this arrow, let me choose yellow, okay? So it goes 2 times in the negative x direction and then 3 times down here. So what is the direction of this vector? Well, from the x it's 2, and it's just not just 2, it's negative 2. And in the y, it's actually negative 3 because we're going down. So we move left and then we move down. Left means negative x, down means negative y. So that's the direction. What about the magnitude? Well, the magnitude is again negative 2 square plus negative 3 square, and that's going to be again square root of 13. So the magnitude gives you some information, but the direction gives you a lot of information. From the direction, you can actually derive the magnitude. But the direction might not always be given to you in this form. All right, they might give it to you in a different form. Now you might be confused, what kind of form would they give it to us in? Well, let's see an example to understand that. So let's say you're given that the direction is 3x hat plus 4y hat. And now you might be confused. What does this mean? And I'm going to talk about that. And the magnitude is equal to, let's say, 100, okay? 100 only has 2 zeros. So how do I graph or represent this? Let's draw that out. So that's the x-axis, that's the y-axis, the x hat, y hat. I'm going to get to that in a minute. So I'm going to just make a couple of points. Okay. So x hat just means, it's a unit vector. It means one step. So x hat represents just one step in the x direction. And y hat represents one step in the y direction. So 3x hat would mean 1, 2, 3, 3 steps. 4y hat would mean 4 steps in the y direction. 1, 2, 3, 4. You see that? And then whatever that comes to, that is my direction, but that's not my magnitude. All right, this is just a direction. Magnitude, they told us, is 100. So what does that mean? Okay, I have this arrow, and this arrow actually, we can calculate the magnitude of this arrow, but it's not the magnitude of the quantity we're interested in here, all right? So the magnitude of this, well, if this is 3 and this is 4, it'll be 3 square plus 4 square, square root of that. So that's 9 plus 16, 25. Square root of 25 is how much? It's 5, right? 5 times 5 is 25. Okay, but they told us magnitude is 100. So to make life a bit easier, let me change 100 to something that's more easy to deal with. Let's change it to 10. All right, let's say the magnitude is 10. So that means this is only 5 though, so we need 5, an additional 5. So that means it's twice the length of this arrow, so we just have to extend it out. And that would be what this vector actually looks like. Now, if you're confused, don't worry. I'm just trying to make it kind of clear a different sort of notation of writing. Usually, I think you're safe to have this sort of pair, and the pair contains the direction as well as the magnitude. But it's helpful to think about things in this way as well, especially if you're, I don't know, the textbook you use or the course you're following uses the x hat and y hat notation. Some textbooks, instead of using x hat and y hat, will use I hat and j hat. It means the same thing. They're just different letters, but it really means the same thing, okay? It's just, I hat is just a unit vector that means one step in the x. J hat means one step in the y. All right? And if you have a negative or positive sign in front of these, like if you had a negative 3 over here, that would mean you're taking 3 steps to the left instead of going 3 steps to the right. And then 4 steps up would still be 1, 2, 3, 4, and your vector would be in this direction, okay? So I'm just trying to show you how you would graph that. All right. Now this is called the Cartesian coordinate system. We make use of x and y's, and they form this nice grid boxes. That's how I like to think about the Cartesian coordinate system. We also can represent the same idea using another sort of coordinate system. And this is, you might not be very familiar with this, so it might be a tad bit confusing. So now we're going to discuss another coordinate system. It's called the polar coordinate system. Okay, so polar coordinate system. And I'm going to explain the polar coordinate system in terms of the Cartesian coordinate system. So you might be a bit confused. But since most of us start off learning about coordinate systems in terms of x and y's, we're pretty natural with Cartesian. We're okay with grids, right? With square grids. But now we're going to talk really about circular grids, which is a bit interesting. Okay, so remember we talked about x and y earlier, and let's just choose a random point here. All right, so let's go back maybe with that previous example of, let's make this 4 and let's choose 3, and we have a vector, an arrow, sort of, that's like that. All right, so this is in Cartesian coordinates, we would just say 4, 3 is this point, right? That's great. Now in polar coordinates, we want to represent, we want to have a pair, but we don't want x and y. We instead want to use an angle and the length of this arrow, whatever the length of, and we'll call that r, okay? So r and this angle is called theta. That symbol, it's a Greek symbol and it's called theta. So instead of using x and y, by the way, this is x, and this is y, we want to now make things in terms of r and theta. And it's a different way of writing things. It's pretty cool, actually. So let's take a look at that. So how would I convert this? Well, first of all, what is the magnitude of this line over here, this golden arrow or this yellow arrow? Well, we already know x squared plus y squared and the square root of that. We already learned that. So it's 4 squared plus 3 squared and the square root of that, which is 5, okay? So this is 5. Well, that's r. R is equal to 5. R is just the length of whatever arrow you're drawing from the origin. So that length is 5. So we already found r. Awesome. Now the tricky part is theta. How do I get theta? Now I'm going to introduce a new concept. You might know this, you might not. It's from trigonometry. Since this is a right angle triangle, we can use something called sine and cosine. All right, and if this is something new, I'm going to define it, and based on this definition, you can pretty much solve it however you want. So sine of theta, it really represents a ratio of the sides of the triangle. So sine theta means opposite by the hypotenuse. So that's opposite is 5, and the hypotenuse, which is this quantity here, sorry, the opposite is not 5. I did not write that out clearly. Let me redraw the triangle over here. Maybe I'll do this at the bottom so it's clearer. So remember our triangle from before? That's a pretty bad triangle. Let's draw a better triangle. Okay, I'm going to try to get this triangle right. Okay, this is a decent triangle. So this is a triangle, and the quantities we had was 4, 3, and 5. So let's put those in. So 4 was down here, 3 was there, and 5 was here, right? Let me just make sure I got that right. Okay, so that's 5, 3, and 4. All right, and this is theta. So sine of theta is defined as the opposite side divided by the hypotenuse. Opposite, by the way, is whatever's opposite to the angle, which is that side there. And hypotenuse, well, hypotenuse is what's opposite to the right angle. That's that one. So the opposite is 3 and the hypotenuse is 5. And so to solve for theta, you would do theta is equal to sine inverse of 3 over 5. And if you're getting worried, just use your calculator. If you have a scientific calculator, you can easily do sine inverse. Some calculators call this as arc sine, okay, of 3 over 5. It's the same thing. Sine inverse and arc sine mean the same thing. On the other hand, we have cosine. So cosine, you can use sine, you can use cosine, or you can use tangent. So these are different ratios of angles, all right? So cosine would just be adjacent by the hypotenuse. So that's what it's defined as. So you're not expected to know this off the top of your head. This is a new definition if you don't know this. So adjacent by the hypotenuse. So in this case, the adjacent is what? It's 4. Adjacent means adjacent to the angle, 4, and the hypotenuse is 5. So 4 over 5. And then we have another one called tangent. So tan of theta is equal to opposite by the adjacent. So that's 3 over 4. Now, it's hard to remember all these formulas, so I try to use the acronym TOA, so. And if you're like, what is this? Well, toa ka so, each of these represents a side. So tangent is opposite by the adjacent. Ka, which is cosine, is equal to the adjacent divided by the hypotenuse. And sine is opposite divided by the hypotenuse. So that's toa ka so. People have different acronyms. Anyway, the point I'm trying to make is all of these can be used to solve for theta. So you can use whichever one you want. You don't need to choose any particular one. You can choose any. You can choose sine, you can choose cosine, you can use tangent. Now, usually when we're converting from x to y, let me try that again. So since we're converting from Cartesian, which is x and y, to polar, which is r and theta, we want to make all of these quantities in terms of x and y. What I mean to say is, this 5 is technically r, the 4 is x, and the 3 is y, right? So if I rewrite these formulas, maybe I'll rewrite them at the corner. Sine theta, remember toa ka so, is opposite by hypotenuse. Opposite being y, hypotenuse is r. So that contains r in it. We don't want theta's definition to contain r. We want theta's definition to only contain x and y. So we can directly convert. If you have x and y known, we can directly get theta without worrying about what r is. That's the idea. So let's try cosine now. So toa ka so adjacent by hypotenuse. That's x over r. It's still not good enough. What about tan? Toa, right? That's opposite by the adjacent. This is our winner. Theta is given in terms of y and x. So this is going to be our formula, all right, for theta. So in this case, it's 3 over 4. So tan inverse of 3 over 4. You have to use a calculator or something. Tan inverse of 3 over 4 is theta. All right, and that's how you convert from Cartesian to polar coordinates. Now, this is not a math class, so I'm not getting into the details. If you didn't get any of this, and it's like you're kind of confused at this point, and maybe you regret watching this video, I'm just going to give you the formula straight up, because this is something that you should learn in trigonometry. Alright, so if I'm trying to convert from Cartesian, let me not even use Cartesian. Let me use simple terms. If you're converting from x and y, to r and theta, r is equal to square root of x squared plus y squared, distance formula. Theta is equal to tan inverse or arctan of y over x. Both of these you can easily plug into a calculator. If you're converting from r and theta now to x and y, which might be the case, sometimes you might get quantities in terms of the angle and the magnitude instead of just getting x and y coordinates. In that case, you can write x is equal to r cosine of theta. I don't know why this isn't working. R cosine of theta, and y is equal to r sine of theta, okay? And if you're curious about how I got these formulas at the bottom, just scroll up and you can see it right over here actually. If you just move r to the other side, x is equal to r cosine theta, move r to the other side, y is equal to r sine theta. So it's pretty nice. Play with these. I remember when I first learned these identities, the sine, cosine, tangent, I was like, wow, okay, I had to understand this stuff. Why does it behave this way? So play with right triangles. They really have a lot of insight, and they really help solve these sort of vector quantity related problems. Okay, that's all math related things. I'm not going to talk about math anymore. I want to talk about motion in 2 dimensions. So let's get into that. So what is motion in 2 dimensions? Well, motion in 1 dimension was being allowed to only move in a straight line. So you can either move forward or backward. Now, motion in 2 dimensions is motion that's constrained to a plane. So a plane would mean, okay, if this is my plane, all right, a little sheet, one could move this way, this way, this way, this way, anywhere on this plane. We can't move out of the plane, like up and down. Okay, that's not allowed. So we can only move in the plane. That means motion constraint to a plane. Now, you can move up and down if your plane is made in such a way, okay, that you can have up and down motion, but then you can only move side to side. So maybe you're going up and then you're going sideways, but then it wouldn't be allowed for you to move this way, like out of the plane. Again, it's only 2 dimensions. If you want a move out of the plane, if your motion needs to do that, go for 3 dimensions. I mean, how can we relay what we learned from the previous class where we had all these cool formulas? How do they apply here? Well, I think the best way or the easiest way to understand this is to just take an example. So the best example, or the most popular example at least, is projectile motion. A projectile is just like a ball that you might pitch, right? So how does that work? Well, typically if you throw a ball starting from here, and if you actually like look at the kind of path it traces, it's kind of like that. And I don't want to give it away, but it's actually a parabolic path, all right? Technically, this is motion in a plane, right? Because it's only moving forward, upward, or downward, right? It's not moving out in a sort of other motion unless you throw the ball in a weird spinning sort of way. I don't know how you would do that, but technically it's a plane. So we're going to say that this plane is in the y and x sort of axes, all right? We're not including z over here for those of you who already know about z. We're going to do that perhaps when we do 3 dimensions. All right. So how do I want to calculate a couple of things related to this projectile's motion, right? I want to know what's its maximum height. How high does it go? So I'm going to represent maximum height by a big H. I want to know how far it goes. So that's called range. Lastly, I want to know its time of flight. That is, for how much time was it not on the ground and just up there in the air? So calculating these quantities might seem a bit challenging, but I assure you they really aren't. And it really gives a lot of insight on how to use vector quantities in 2 dimensions. So first, let's see what's given to us. Now, usually what's given to you is something that you can easily measure in reality. So what's given to us is the velocity. And not just any velocity, it's the initial velocity, okay? Because the velocity is going to change. If the ball goes here, it's going to change. If it goes here, if it goes here, velocity keeps changing depending upon where you're at. So we're going to be given the initial velocity, so we'll put an I there. And the initial velocity, yes, you can have it in terms of x and y coordinates or in terms of r and theta coordinates, meaning in terms of Cartesian or in terms of polar. For this exercise, I'll show you how you can do it in both. So let's say the velocity, the initial velocity, is given to us in terms of r and theta. Okay, so if it's given to us in terms of r and theta, now in this case r will actually just be a v. So we can just say r is v. So I'll say v and theta. So v is the magnitude of the velocity, like a number without any sign to it, and theta is the kind of like the orientation with which you throw it. So vx would equal to v cosine of theta, remember the previous formula, and vy would equal to v sine of theta. That's if you need vx and vy. Otherwise, you could just leave it as v and theta, where v is this initial velocity that we're throwing the ball at, and theta is what angle are you pitching it at. So it's more clear, I think, and it's in terms of v and theta. X and y just make it a bit more complicated. But for our purposes, we're going to actually solve the equations in terms of x and y. So v and theta, so v could be 5 meters per second, for example, and theta might be like 10 degrees. All right? So that's just a quick example, but I'm going to solve everything in terms of variables. So those are our velocities, and these are initial. Okay? So I want you to be clear on that. These are initial velocities. Cool. Okay, so let's try to first solve for the maximum height. So the red quantity. What is the highest the ball can go, given a certain velocity and given an angle theta? Well, to answer this question, we first need to ask ourselves, what is the acceleration on the ball? And I know that I haven't talked about forces yet, but let's just analyze a ball, right? If you just throw a ball, what do you think's affecting the ball's motion? Well, we have gravity, of course. I'm going to call that minus g. it's a negative acceleration, right? It's going downwards. If it was going upwards, it would be a positive g. But gravity doesn't act upwards, right? Otherwise, we'd all be, I don't know, we wouldn't be on Earth anymore. And then we've got air resistance that's pushing the ball in the opposite direction. And the ball's trying to move forward, with air resistance moving it in the backward direction. But for our purposes, air resistance makes things complicated. It's not that significant. At least we're going to assume it's not too significant. So we're just going to ignore air resistance. Now, gravity is technically acceleration, right? We call it acceleration due to gravity. So gravity is acceleration. Acceleration is a vector quantity. That means it has to have a direction. So what's the direction of acceleration? Well, according to our diagram up here, we decided that x is going to be the sideways. Did I mention that? I don't know if I did. X is going to be the sideways motion. So I'll just make a small little diagram here. And y is the up and down motion. So, and gravity acts downwards. Therefore, gravity is in the y direction, right? It's in the minus y direction. Does gravity have any x component? No. Are there any forces in the x direction? No. Air resistance is, but we're ignoring it. So there are no forces in the x direction. There are only forces in the y direction. This is awesome because now our formulas look a lot easier. So if I want to get maximum height, that's easy. I already have a formula for that, by the way. So just to recap, AY is equal to minus G and AX is equal to 0. All right, there's no... And the y velocity is constant. It's not changing. So we can use these formulas. Remember, S is equal to ut plus 1/2 at squared. So I'm going to transform this equation in terms of the y directions only. Remember, this was a one-dimensional motion equation. So one dimension means motion along a straight line. Well, we have two lines, right? We have y and we have x. We're only going to consider everything that's happening in the y direction. So all these quantities here are going to be translated in terms of y. So since we're solving for height, height is only in the y direction, right? That's how you measure height. You're not measuring height in the x direction. So you can call it S as h. Now what would u be? U represents initial velocity. We only want the initial velocity in the y direction. And remember, that was given to us up here. Vy was equal to v sine theta. So we're just going to take that. So v sine theta. Now time. Is time in the x or y direction? No. Time is always just time. It's universal. Well, at least for now. So this is all times time plus 1/2 a. A is acceleration. What is the acceleration in the y direction? We already talked about this. Minus g. So we just put minus g in there. And then t is just t squared. That's it. You have the formula for the height. And you might be wondering, wait, where, how? Well, v is given to us, theta is given to us. T isn't given to us, right? So we don't have the value for height yet, because we don't know how long the projectile is airborne for. We don't know that quantity. What's given to us is v, theta, and we know g because it's a constant. We don't know anything else, so this equation isn't good enough. Let's try another equation. Another equation that we had was v squared is equal to u squared plus 2as. Let's convert this to y quantities. So v squared is the final velocity in the y direction. I'm just going to call that vyf, okay? It represents v in the y direction, that's final, is equal to u squared, which is just v sine of theta, that's what we had, minus 2gs. I just took the negative sign out. And s is just h. All right, now I'm going to do a bit of magic. How many of you have seen balls thrown into the air? Obviously, most of us. I think all of us. When the ball is at its highest point, do you notice that it just stops there, and then continues going? It doesn't move any higher. When it's at its maximum height, when the ball is at its maximum height, its y velocity is actually 0. It has x velocity. It's moving this way. But its y velocity goes to 0. So Vy at this point is equal to 0. Vx is still Vx. Vx is not going to change. So I can say this is 0. And that allows me to solve for h, right? Remember h? So h is equal to v squared sine squared theta divided by 2g. And that's how you calculate the maximum height of a projectile. So that's the first quantity that we wanted to solve for, right? And that's pretty awesome that we got it. Now, what's the next quantity we want? Let's go back up there. All right, so we got h. I should have kept it as capital H. Well, capital and lowercase h, they mean the same thing, okay? Now, if you look at this graph, there's a big hint. It's actually really showing you something interesting. This whole thing over here and this little portion over here, they're symmetric, they're equivalent. So the time it took for the projectile to reach its maximum height is just a half of the total time of flight. So if you just take, okay, how much time did this projectile take to reach its maximum height? If you solve for that, then you get a certain time. Well, double that time and it's just the time of flight, because this is exactly symmetric, right? It's a symmetric graph. So you had to use geometry, you had to use tricks. That's the easiest way I'd say to solve physics. Okay, so we want to solve for time now. So remember this formula we had before, and I tried using it, and then, oh no, we didn't know what time was? Well, now we can use this formula and actually solve for time. And for those of you who are actually really looking at this, you can already see that we have two time variables, and you might be wondering, how are we going to solve for this? Well, we're going to have some fun with quadratic equations. So let's plug in h's value. H is v squared sine squared theta divided by 2g is equal to v sine theta t minus 1/2 gt squared. That's just the previous formula. I substituted h here in that h, and I just wrote the whole formula down here. All right, so let's write this quadratic equation out. I'm going to reorganize this a bit. So I'm going to multiply 2 on both the sides, and I'm going to move this g and this v sine theta all to the other side, so we have a 0 on the right side. So now we have gt squared minus 2v sine theta t plus v squared sine squared theta divided by g is all equal to 0. All right, I'm going to just brute force my way through this. There's maybe an easier way to solve this, but I'm just going to go use this, all right? So let's see. Remember, minus b plus or minus b squared minus 4ac divided by 2a. That's how you solve and these are what the intercepts are equal to. Well, that's how you are going to solve this equation. You might be confused, what does this mean? Just take the t's and make them into x's and you'll see what I'm talking about. And what are these b's, a's, and c's? Well, if you're confused about what these things mean, just remember ax squared plus bx plus c is equal to 0. Make t's as x's, and whatever these constant values are, they're just b and c, okay? And that's all you have to really do. So let's plug those values in. So a is just going to be, okay, so b is actually the real tough one over here. So minus of minus b, so the minuses go away, 2v sine of theta. Don't include the t is x, remember, you don't include that. B is 2v sine theta, plus or minus, all right, so I managed to write down the whole thing. So t is equal to this very interesting quantity over here. And if I'm not wrong, this g and this g cancels out. 4v squared sine squared theta, sorry, I can't speak. 4v squared sine squared theta minus 4v squared sine squared theta. Both of these actually cancel and give us a 0. So this is interesting. T is equal to 2v sine of theta divided by 2g. I'm going to verify all these equations. I'm just doing these without even looking at my notes. So yeah, this looks like what t should be. Okay, and remember, this stands for initial velocity, okay? The v over here. Maybe I should put a little I next to it, I don't know. But I want to keep things simple, so I'll leave it as is. So that's, oh, I can cancel out the 2's, so it's just v sine theta divided by g. But wait a minute, this is time for reaching the maximum height, it's only half the distance, or only half the time. So technically, this is wrong. I have to say t is equal to 2v sine theta divided by g. It's twice the time, because this time represents the projectile reaching this maximum point, but then we still have the other half of the journey to go. So how much is that? Well, it's just this over here, so it's twice, 2 times, whatever that is. All right, so this is the actual correct formula. All right, 2v sine theta divided by g. Okay, now the last one, the range, right? Well, okay, we've done a lot of math here. The range, maximum range, this is the hardest one. It's so hard that we're probably going to spend another hour just deriving maximum range. Now, what is range? Range is, okay, projectile is moving, right? Whatever. Range is the distance that was covered on the floor. So if the x direction, right? The x distance. For our purposes, there is no ax acceleration. It's 0. So we can just use our equation v is equal to x over t. V is equal to distance over time. And in this case, v is the v in the x direction. So let me put vx down there. So vx, remember, is v cosine theta. And x, in this case, is r. And t, what is t? T is the time the ball was going through its journey. And wait, from the previous problem, we already solved for that. So it's 2v sine theta divided by g. So we're going to put that in 2v sine theta divided by g. And guess what? R is equal to 2v squared cosine theta sine theta divided by g. And if you're really math savvy, 2 cosine theta sine theta is just sine 2 theta. And that's range. I know I said it's going to take an hour, but it's very simple. Once you know the time of flight, getting range is very easy. Because let's look at this formula. It's so simple, right? That's because there's no acceleration involved. So these are equations for one dimension. And we were able to apply them for a 2-dimensional problem by breaking down the problem, a 2-dimensional problem, into 2 separate 1-dimensional problems. This was possible because x and y were not dependent on each other in any way. If x and y were dependent on each other, we wouldn't be able to do this. So the takeaways of this whole exercise were, I think, a couple of things. First of all, like I mentioned earlier, a 2-dimensional problem got split into 2 separate 1-dimensional problems. And you can probably do the same thing if you go into 3 dimensions. You can take a 3-dimensional problem, split it up into 3 1-dimensional problems. But that's only allowed if all these variables are independent of each other. Okay? All the y's easily go together, all the x's go together, all the z's. We didn't talk about z's yet, so I won't even mention them. Now, we solved all of this in terms of Cartesian coordinates. If you realize, we used x's and y's. We did not use the v and theta at all until it was plugging in stage, right? You can solve the same problem using r and theta if you want. And it's a bit more challenging, but it gives you a lot of insight. So yeah, if you're into that kind of thing, try to solve these problems without dividing it into x and y. Maybe solve it directly as a 2-dimensional problem and then see where that takes you. Another point I wanted to bring out was these formulas, this H formula, the time of flight, the maximum height, the time of flight formula, and the maximum range formula. These formulas, you could easily just remember them and pretty much solve any projectile motion problem. It's not that hard to, but from my experience at least, I didn't really have a formula sheet when I was in high school. So for me, I tried deriving them on the exam in order to solve the problem. So maybe it's in your best interest to try to understand how to get these formulas in the first place, so that when you're on an exam and maybe the problem is just altered a little bit, you don't freak out. You already know the process and you're able to go through it. Whatever works for you in the end. And so that's all I have for today. I'll see you next time.